line here is sort of showing you that it's hinting at the design. So what I'm going to talk about is designing a comfortable contact lens. So the things you could change is you could change the material of the lens. But that's not something that I'm going to change in my model because I'm working with Bausch & Lomb and they have material that they like to use. The other thing that you can change is the thickness of the lens, and that's why I really like this picture, because you can sort of see there's a transition here, and I believe what's happening is they're changing the thickness of the lens there, and you can see that happening. And they can also change the shape of the lens, right? So how you could think about how curvy it is, or its curvature. They can change. And so I'm thinking about soft contact lenses. So when they sit on your eye, a soft contact lens will go over what's called the cornea, which is sort of the clear part of your eye that lets the light in, where your pupil is and your iris. And it goes onto the white part of your eye, which is the sclera. So this is sort of how a contact lens sits on your eye. It's completely immersed in tear fluid. So underneath the contact lens, it's about two microns thick, and then sitting on top is a couple microns. And just to give you a sense of the scale, here the contact lens is much thicker than the tear film. So that, again, the tear film is a couple microns, and then the contact lens is anywhere between 50 to 200, 300 microns sitting on top. So this is sort of the configuration. And the contact lens, what it does is it pushes and pulls on your eye based on the design of the lens. And we think that that is linked to comfort. So the reason why we're studying this problem is because 30% of people stop wearing their contact lenses because they're uncomfortable. Right? So we want to try to minimize that number. So what I'm showing you here is they use a machine that's called an OCT machine, and we have two different lenses. So this is one lens design, and the other row is another lens design. Can you guys see that the top lens, what you're seeing is the edge of it pushing on the ocular surface. Do you see the edge of the top lens is round and thick? And do you see the edge here, this contact lens is pointy? Do you guys see that? And it's pushing on the surface of the eye. So this is just looking like they took an image of the white part of your eye to see. And this person wore their contact lens for 14 days. And so they came back and re-imaged the person's eye. And this is what happened after 14 days. Do you see that on the top there? Do you see that the big, thick, round contact lens really kind of buried into the ocular surface and made a divot? Do you see it there? And the pointy lens didn't. So this is just to try to give you some intuition that the edge, the lens design, the shape, and the thickness matter. And there's really this sort of give and take where you don't want the lens to be too thick because it can push on the ocular surface and cause these indentations. But you can't have it be too thin because can you imagine every time you blink it could roll back? Right? So you have to kind of play this, there's this give and take. And so the question is which lens design is better, and then you somehow have to describe what better means, right? So I think better means comfortable, but I also think better means safe, right? You don't want to damage someone's eye. And so what I've been working on is to try to quantify how hard this lens is pushing and pulling on your eye, given its design, given its shape, and its thickness profile. So that's my quantifiable question that I'm trying to answer. And so I am going to just share with you one calculation that we did to develop our model. So when we start with this really big, messy problem, just like you guys had to do today, you have to start by making a bunch of assumptions, right? You have to decide what's important and what's not important, right? So the idea is when you're writing your model or building your equations, you don't want them to be so complex that they're so hard to solve and you don't gain any insight, right? So you want to build the simplest model, but it's got to get it's got to capture the essence of what's going on. So there, again, it's an art, trying to find this balance. So the first thing that I usually do is I do a lot of back of the envelope calculations. And so I'm going to share one with you. And this is work done with my colleague David Grass, who some of you might have met over the years. So this was the first little calculation we did, is we thought, let's just take a strip of the contact lens material. Let's stretch it a little. Let's put it on the tear film. And let's see how quickly it goes back to its original shape, right? So this is an elastic material. So imagine in your head you have a rubber band, you have stretched it, you put it on water, and you want to watch how quickly it goes back to its original shape. That's the thing I'm trying to quantify, is that motion back, and how long that takes, okay? Okay, so now we're in this sort of formulation phase. We have our problem, right? We know what we're trying to quantify. We're trying to get our handle on that time. How long does it take? So now we start to think about what are the things that matter and are important in this problem. And so I start to name them and give them names, right? So I think some things that are important about the lens is how long is it? So I'm going to call D the diameter of the lens, okay? So I'm not going to have my lens be curvy in this calculation. Imagine it's just a square strip of material, right? The same material, but it has the right diameter D. And again, I'm not talented with PowerPoint, so this contact lens should be a 3D image. And so it has a width W, which is represented by that arrow. Can you imagine that it's going like this, 3D? Does it? Okay. It has a thickness. I'm going to call that thickness tau. So what I'm introducing are what are called parameters, right? Because I want to be able to change them, right? I want to be able to change them, and I want to understand, well, if I make my lens thicker, what happens? If I make it thinner, what happens? So I just introduce what we call a parameter, and I name it. I call it tau, and then later on, I'll put a number in for it. And then I have my thickness of my tear film here, H. Okay. The other things that I'm trying to tell you, well, I'll introduce the other parameters as we go along. So imagine in my experiment, remember what I'm doing is I'm taking my contact lens and I'm stretching it, okay? And so I need to describe that stretch. I need to name that thing. And this thing is a variable because it's going to change with time. Okay, that's the thing I want to keep track of. So I want to understand, I'm going to have S. S is my variable. It's going to change with time. It's tracking the motion, right? How stretched is my material. And S is eventually, I'm thinking, going to go to 0 based on my understanding of the experiment. And I want to know what time, how long does it take to reach 0. So I name that thing, and that's my variable. That's the thing I'm trying to keep track of. That's the thing I'm going to build an equation about so I can solve. Any questions so far? No. Okay. All right. So okay, there's a lot on this slide, but let me try to explain it to you. Your equations are encoding behavior. That is what they do. They're encoding some behavior. So this problem is fundamentally rooted in physics. So the behavior I'm encoding is Newton's second law. Do people remember Newton's second law? So mass times acceleration equals the sum of the forces acting on my contact lens. So that is what my equation encodes. That's what it says. And so now I have to mathematize that, right? I have to describe mass and acceleration and forces in terms of my variables and my parameters. That's what I'm trying to do here. So what I'm going to do is if those of you have had the pleasure of taking physics, you remember you drew free body diagrams. And you had a control volume with you balancing forces on, okay? That's what I'm doing now. So my box here, this is my control volume, and I'm going to balance forces on this box, okay? So this chunk of contact lens material, it has a mass, and it has an acceleration that I'm trying to predict. So here is my little box. I just chose it to be a fourth of the stretched material. Does everyone see that? Because D is the original diameter, S is how much I pulled it out, right? And then I divided it by 4. Now, I'm going to introduce my coordinate system. I'm going to put my coordinate system, this is a choice you can make, I'm going to put it in the middle of the contact lens, right in the center. Because when I stretch my contact lens material and I let it go, intuition tells me the center is not going to move. This thing is just going to come in. So I'm going to put my axis my origin right in the middle of the contact lens. And so here what I'm doing is I'm describing any position of my lens material. So X is describing, if I drew a line here, where it would be at time t, right? So X naught is its original position before I stretched it, and everything gets moved by the same fraction of amount. So this is tracking any point in my material after I have stretched it, okay? Now, because I need to describe the mass times the acceleration, I need to think of this body as I need to keep track of the center of mass of that chunk of material, and it's going to be right in the center here. So this is my center of mass. This is where the center of mass, this is the position of the center of mass, right? So what I did is originally it was at position 3/8 of D, right? And this is the percentage of which I stretched it. And S is the thing I don't know, right? That's my variable I'm trying to find. So if I have a position, how do I get an acceleration from a position? So I have a position, then I take a derivative of my position to get a velocity, and then I take another derivative to get an acceleration. So if you see, inside here is the acceleration. I took two derivatives of this position. Do you guys see that? So this is my acceleration. So I have mathematized acceleration. Okay. Now I need to mathematize the mass of this material. So I'm going to take the density of the material and I'm going to multiply it by a volume. Okay. And here is the density of my material. And the volume, right, so it has a thickness tau, it has a width w, and this is the length of my chunk of material, right? Right here, this is its length. W is its width, tau is its thickness. So I have mathematized the left side of my equation, mass times acceleration. I need to now mathematize the sum of the forces acting on this. Is everyone okay so far? Okay. Now, I have to introduce a little more physics to you. There are fundamentally two forces acting on this chunk of material, right? So you guys, there's the fact that this material is elastic and it wants to go back to its original state, its original shape. Right? So that's the elastic restoring force. But this is not happening in a vacuum, it's happening on fluid. And you can imagine if I did the experiment on water and I did the experiment on honey, do you guys think I would get a different result? Yes. Why would I get a different result? Does anyone want to?
Because the liquid you're doing it on also is exerting a force.
That's right. The liquid I'm doing it on exerts a force, right? And so that force that it exerts is called a viscous drag, which I'm going to quantify next. And it depends on how sticky the material is, or its viscosity, its internal friction. And we know that honey is really sticky, so it has a large viscosity. That's the way we measure the stickiness of it. Okay. So that's the first thing we're going to quantify. All right. So the first thing we're going to quantify is the force from the fluid. So the fluid is going to try to slow down this contact lens chunk of material to going back to its shape, right? It's like pulling on it, right? And the way that we quantify how it's pulling on it is we use this equation of state that's true for our fluid, right? So what I'm showing you up above is that imagine you had an experiment where you had a tank of water and you had a surfboard on top and you wanted to move it with a constant velocity. You have to apply a force to that surfboard to get it to move at a constant velocity, right? And that force that you're applying is called a shear stress. And the way we mathematize that is right here. It depends on how sticky the fluid is underneath. That's the viscosity. That's a parameter that depends on the fluid. And it also depends on how fast you're trying to move the surfboard. Doesn't that make sense? So this one is, imagine you were standing in a big bathtub, right, of a fluid, and you had a surfboard and you wanted to move it at a constant speed, V. So again, the fluid underneath would change how much force you would have to add. If it's honey, you're pushing harder, right, than compared to water. And that's what's being mathematized with that parameter mu. It also depends on how fast you want to go, right? So V is the velocity, and it also depends on how much water you're standing in, okay? So you have to add more, you have to exert a higher force when H is smaller. Okay. Now, this is what's called a shear force. So it is described as a force per unit area. So what you're going to see, this is just another picture about where the idea about where this happens. Essentially what you have to do is the fluid at the bottom has speed 0 and the fluid at the top has a speed V, and you have to try to drag this, right? You're trying to drag the fluid all along to make it the same speed V on top. And so you're exerting a force on the plate, right? And the reason why you have to exert that force on the plate is because the fluid is fighting against you, right? And that's what this arrow is showing you. The fluid is trying to hold it back, right? Okay, so this is our force, okay? Let me try to write again. This is tau, okay? Okay, so it moves in the opposite direction to the speed of my chunk of material. So that's where the negative sign comes from. Here's that mu. This is V, right? Remember, V is the derivative of my position. And this is H, which depends on how thick it is. So this is a force per unit area. So I need to multiply it by an area. And here is the area at which this force is acting on. It's the bottom of my little chunk of material, right? It has a width W and a length D plus S over 4. Now, in math, what I can do is I want to build the simplest model. And in my experiment that I'm doing, S is much, much smaller than D. Right? So imagine you could explain to a student that this is 1 and this is 0.001. So this term doesn't really matter because it's dominated by the D. So that's why I say I can get rid of the S and simplify things. Okay. Now, the other force is the idea that the material wants to go back to its original shape. If any of you have heard of Hooke's law, or how a spring behaves, that's what I'm encoding here. And so what I'm saying is that the force at which I have to, so imagine I had my spring or my chunk of material and I stretched it out, I have to apply a force on that. And so the reason why I have to apply a force is because the material is resisting what I'm trying to do. It wants to go back to its original shape. And the way I quantify that, right, is if you're used to seeing in your physics class, it was usually presented to you as K times X, where X is your displacement and K is the stiffness of your spring. I'm going to present it in a slightly different way, right? So again, S is my displacement. That is how much I stretched it. But rather than using K, I'm going to introduce something that's called a Young's modulus, which tells you, again, how stiff the material is. The reason why this formulation is more robust is because if I made the exact same spring, but this one is longer than this one, the K's would be different, right? So the stiffness that you're used to seeing in Hooke's law depends on how long your original spring is. I want to move away from that. I want to have a material property that doesn't matter how long my strip is, right? So we introduce what's called the Young's modulus, right? which is related to K. And that's what's happening here, okay? So again, you can think of this term as K and this term as your displacement, but that is what the elastic restoring force looks like. And again, this is a force per unit area, so I have to multiply by the area it's acting on. So again, it's acting on this face. Okay. So I have 2 minutes, so I'm running out of time. So I put all these things together, right? Right, so I have my mass and my acceleration, and then I add up my forces, right? That's what my equation looks like. So I created an equation for S. It's a differential equation. So the answer is not a number, but a function. Okay, so now what I'm going to show you is these are all the parameters that are relevant for my contact lens. So you see this parameter is 10 to the minus 4 sitting in front of the acceleration. This is 10 to the 4th, and this is 1. So what we do what I'm going to do is, there's a beautiful theory to do this, but I'm going to ignore this second derivative term. I'm going to say it's small. Because again, I want to build the simplest model. If I assume that's small and I rearrange my equation, then I have a differential equation that we have all seen before, because the answer is an exponential function, right? So it's the function whose derivative is a multiple of itself. That's the exponential function. And so that's the answer. That's how my position will change with time. And I wanted to know how much time that would take, right? So the way we estimate that, usually in applied math, is we think about how long it would take for S, right? We basically make this coefficient equal to 1. So we figure out how long it takes to take our original position and divide it by E. That's usually the characteristic time. We call it, this is our relaxation time, on average how long it would take. Okay? And so if I figure out that time, so I took the reciprocal of this, I get 10 to the minus 5. So what that means is this thing is gonna just snap right back. You're not even gonna see it happen. You have to have a really high speed camera to see that happen, right? So what that means is when I go to build my model, I don't need to worry about the fluid. I don't need to worry that it's tugging on the contact lens, because it's not winning, right? What's winning is that elastic restoring force. So I can build an even simpler model. So this is just one calculation we did to build a very sophisticated model. And so I am out of time. And so should I stop?
If you're okay with me posting the slides,
Yes.
then yes.
Yes, so I will stop. And again, I'm sorry that I have to leave right after this, but I will come back to lunch, and I'd love to have, I don't know if there's something planned during lunch or if people get to network.
Time for you to sit with people that would love to hear more about it.
Okay, great. So I look forward to having more conversations with you all at lunch. Thank you.
Okay, thank you, Kara.